Bismillahirrahmanirrahim. This is Harish Hussain. Hello everyone. I just do this tutorial, which basically I do for myself, but I may share later on YouTube for other people how you analyze a three-story building with a cooling tower on the top and an impact load on the side. So basically what I have is a three-story model. On the top, I have a cooling tower that generates pulsating axial load. And on the side, I have an impact load on the one of the first floor's column. So I use SAP for this. I have analyzed it, let's say by hand, technically, using finite difference method. And I'm checking my calcs with SAP. So I share my screen, like that. This is my SAP, it is open here. I have to put this in. So when you open SAP, then check units. I live in the USA, so I go with pounds, inch. And my building, let me show my building. Usually I have two screens, but now I have one screen and everything is mixed up. Yeah. Basically, I just want to show you my model. Yeah. So this is my model at the structures lab at Old Dominion University. I have a cooling tower on the top of a three-story model. It is about 50-inch tall. The bays are 8.5, 8.5, 16.5 each story, and I have a pendulum that hits this middle column. So that is my model here. And at the bottom, this hollow section, 1/2 inch by 1/2 inch, thickness is 1/16, and this can decrease vibration using the sphere bead. So I haven't published anything. Yeah, I have a conference paper on it, but I have a publication on the way on this. Then you guys may have more detail on my talks. So this is the story. We're gonna do it on SAP. Open a new page. New models coming up. My SAP is kind of slow on this computer. That's all I can do. And I also have my forcing functions from the cooling tower and the impact load. The cooling tower I got from the company called Baltimore Air Inc. Is in Baltimore area, around Washington, DC area. And for my pendulum, I got it from the lab. I attached an accelerometer to the pendulum and hit the building or the frame or the model. Then I got acceleration versus time. And then multiply this by the weight of the pendulum. It gave me forcing function. So I usually go with 3D frames. It's a 3D number of stories. We have a 3-story frame. On x-axis 3 bay, y-axis 2 bay. Story height, let's go with 16.5. The first floor is 16.25, but we'll pixelate. The bays are 8.5. 8.5 inch. So that's my lab frame model at the structures lab. Select that high. Let go default, move pixelator. Basically, this is the frame. I just showed you guys. Let me make this 3D. And here we delete everything. First, we edit the grid. Right click here, grid data, modify. Go with spacing. I go with spacing first. Story is 1625 for me. 25. Letter 16.5, 16.5, because SAP goes from center to center. The first starts from the floor, so you're losing a quarter inch there into the center of the second floor. You get a quarter inch there. So total like clear height is 16 inch, a quarter inch on the top, the bottom is flush, the 16.5 the top. It goes half, 16 half, so it's 6 quarters, 16 quarters, so 16.5. Okay, see this should come down a little bit. It did, I don't know if you saw it, but a quick way to check is this to here. She says 1625 on the far right side. And if we go to the second one, it says 16.5 on the far right side, just to check it. Because this, I go kind of fast because I have a meeting, I am at work. I want to do it real fast. Material, I tested my material is steel. I modified this guy here. Mine came out 61. Yielding stress. And I like Gibbs inch, KSI. My youngest models was 28,000. Yielding stress, everything I put in 61. That's what I got. And simplified. Always check your weight in pound food in American standards, 490 pounds for each cubic foot of steel. And I did cut a small piece, like a 13 inch, found the volume, weighed it, then I got 489, which is pretty close to 490. I go with 490. So that's my material. If you want to check your stress strain diagram, it is right here. So it's going up, yielding, fully plastified, and then come down with a drum source. It doesn't show necking or those kind of stuff. I don't go that far. My material is ready. Named it FY61. So now we go to the material 1/2 inch by 1/2 inch. We go to here. Add new property, I think, yeah. Tube, mine is a tube. I just call it lab specimen. The thickness of the wall is 116. 116. Outer dimension is 1/2 inch. 1/2 inch. Here is really important. And go here, you pick your material, odds was 61. And then here, this is ready. Now it is drawing time. Here, pick your material, lab specimen, and then start putting it 16 quarters, 16.5, 16.5. There's so many ways to do this. But I like to do it this way. Now, just be careful, don't put the material in the wrong direction. You don't have time, you can just fast forward the video. I'm doing it for myself, guys. I love to share. And then find any useful video on time analysis, time history. What's that? Sky to the sky. Usually I do it faster. But you know, when you start recording, you get panicked. It's okay. It is completely okay. 8.5. Usually I check it by dimension, you know, if it goes in one direction. And on this side in 3D, you see where you at. Usually people go on like axis views, like one thing you don't like it. So mine is good. Yeah. And then what we do here is the fun part. Select all and then go to edit. If I just look, my XYZ is X is that direction, Z is upwards, Y is to that direction. So I copy this panel to the Y direction 2 times, one here, one here. So I go edit, let's replicate, and the Y direction. My base 8.5 inches, so I put in 8.5. How many layers I want is 2. You see here, this will go here and here. 8.5, yep. We are now in that part. And then we do the top floor. Let's go this guy here, 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 and this. And then we do the same thing. Select the new beams. And we'll replicate those beams to this floor and that floor. And that's on the Z direction on the negative direction going down. So I go on edit, replicate, zero this one out. We are on Z in the negative direction going down. Each height is 16.5. We need 2, because one is to this floor, one is to this floor. Okay, we are done. This is here. And the next thing we do, we flip it over. Why? I don't know why. Boundary condition is fixed, and you can go fancy, select the bottom part of it, and then, but I just want to go step by step. Assign, join, constraints, fixed end. Now probably this fixed end. And now it is the fun part. See, each one is one piece. I will have the pendulum hitting here. I showed you the picture, guys. You see this pendulum hitting the middle of this column? So we gotta put a hinge, not hinge, joint door node here. We have this picture open. So this guy, I cut it into 2 pieces. Define, No, edit the lines, divide frame, divide into two pieces. I don't want to go more. Apply, and see now we have this here, but for the rest we don't have. I don't. Now what we do is we define our load pattern. We have pulse, I call it pulse, call it other, self-weight included, yes, and then the pulses from the cooling tower, and the impact is the pendulum, so I call it impact, same thing. So I have my two loaded here. Okay. Now we try the loading. My cooling tower is sitting on these two inner columns, here and here. So I have simplified it. This is my forcing function from the cooling tower. That Q naught, P naught is self-weight. So here self-weight is 0 from the building. And then that's why I put in 1 when we define the loading. So it includes P naught when it's house to the building. I have also analyzed this column along with spring boundary condition here, and I need the P naught. So my Q naught I divided by 2, half going here, half going here. From the manufacturer, weight of the cooling tower is 3,800. No, 3,890 pounds. No. It is 7,780 pounds for 29-ton cooling tower from Baltimore Air Inc. people. And I've divided it into 2, one going on this column, one going on that column. So when you divide that into 2, it will be 3,890. And that's for a real size building. So my model is a small model. I have decreased that load 10 times. So from 3,890, I went to 389. So I have 389 here, 389 here. And the omega is the frequency, natural circular frequency of the cooling tower. I got it from the manufacturer in RPM, round per minute. I converted it to radian per second. It is 52.88 rad per second. And this is time. This is, we said, weight of the cooling tower. We said this is separate of the load. So here, what we do, a unit load here, a unit here. These two inner joints, assign joint forces. These are pulse. Z-axis is upward, we are going down. So it is, we see -1, and then later we multiply by the time history function. And it includes the 80, something, the 89. So let's apply. It shows it here, but if it doesn't show it, just click on the joint or right click on it, and then loads this pulse on Z direction -1. And then we do this guy. And let me just go with this one. Stay here. We select it again. Assign joint load forces. This time it's not pulse, it's impact. This put 0 and C x-axis is in that direction. So this is our x. So we go on x-axis 1. So it's in this way. So now we have the loading 1 here, 2 up here. Now we put in the time history function. For the time history function, see this equation. We can show you this. This one for a single column, this frame. Synchronize here. This is the forcing function. So this forcing function C, this is the pulsating axial load from the cooling tower. Basically, cooling towers do this from the motor, and the fan rotating does this. So that's your forcing function from this equation. I put it in here. And 389 is K naught, P naught. I put in 0. This is my forcing function. For my impact load, then it's first force column is this guy. It's one hit. Up to 300 comes down, and your time duration is 0.0207 seconds. Somewhere here. And see, I remember it right. There's been a couple more, so I haven't checked this. 0.0207. And I got natural circular frequency of the frame. I'll show you how I get these numbers. Lab frame, and this is very accurate one. I divided each column in each structural number column into 10 pieces. And I ran it yesterday using direct integration for the same thing we do today. And it took about 3 hours to run it. So when we do this, and delta T here in this equation, that T, I divided this into 400 to be more accurate. So my delta is 0.00011148. So basically you copy this for a forcing function and paste it into a text. File. So something like this. This is a notepad text. Select 0890100114444. 395. This is what I selected from this. Copy paste it into. I've already done it. You do the same thing for the impact load. You see, this is the impact load. So for the pulse, putting that equation for the impact is the acceleration equation times the weight of the pendulum, which is 62 pounds for me. That program in a way that it doesn't go beyond 0.0207. And then that's that. You guys know what I mean. Then you come here from SAP, define the time history function. Go from file because you already have it. If not, if you have a sinusoidal or cosine equation, you go here. New. First of all, put this on that guy so it doesn't put in time intervals for you. We call it pulse forcing function. And browse. Where's that file? This stuff for you is here. Also, this is resonance. My name is resonance. This is the equation in the plot. There's two rows. I'll tell you why. So 2 columns. Open this. One column is time, one column is the forcing function. Always check this. This is your detected time. Please write it down. 1.0014. And convert it to user defined. It takes a few seconds to do this. Bear with me. You can fast forward, actually there. Sometimes people explain really important things while they're waiting on the computer program to run. So, waiting. Again, this is for the cooling part. So we are waiting for a time history forcing function for this part. And that is from here, is this part, which is, this is the plot of it, but in SAP it just showed as a blue rectangular section because it compacted the graph. This part is up to 11 seconds. I'll have it at the top as well. 11 seconds. See now, set time, value 0s, 89. It goes on and on. I could check here, see that my cruiser is directly shows here. This time, that's the forcing value. We go okay, and that takes a few seconds as well. For patterns, we do the same thing for this. We copy it, put it into your notepad here. 0, 0, 0, 0, 1, 1, 4. It is that much. Up to 0.0207, just somewhere here at the ends. So when it exceeds 0.207, then put 0. And I think it is ready. So much. Maybe it wants us to wait here. But again, this time function is on this axis and that axis. The next one we do is for the impact load by here. I don't know why it takes so much time, maybe because I opened something else. Yeah, it is see, also here. Now we go the same thing from file, add new. This time, impact forcing function. Browse impact. This is your impact. This is 2. You see the file is all uploaded. Convert. This one goes faster because there's not much data. My impact is starting to. Now, we go here, load cases. For doing anything for a model, find natural circle frequency, I go with RITS. I don't go with eigen, I go with RITS. Just 5 models is enough. This is acceleration. Added. Dynamic precision ratio 99%. So, and here, when we go back, that included mass. And the pulse, modify. We go to time history. And we do linear model. Yesterday I did that integration. It took like 3-4 hours to run. The model, linear, pulse. The time history function is we put it in to modify number of times. Because here we do a calc. So in Excel sheet, this is our data time 0.0001148. We put back in here, 0.000148, and I want to run it for 5 seconds. So 5 seconds divided by 0.000148. You can do it on SAP and just say 5 divided by 0.000148. I don't like it this way here because, well, let's do that way. And here, I put damping. I've calculated my damping for this using log decrement. It was 0.0001%, but in SAP you gotta put twice of it because there's a viscous damping to the other damping. So 0.002, which is good to go. We do the impact load, modify, same kind of procedure. Time history, linear model, we did that integration, takes more time, but more accurate. Just say that. Impact is impact. Modify, same thing from 0.000148. Gonna run for 5 seconds. So that is telling you how much time you need when you run your SAP. Based on these steps, SAP goes through the loop again and again and again. If you want to run for 10 seconds, you need twice as much time as you need for 5 seconds. This is 0.02, is based on your model, whatever you put it in here. Okay, that's ready, and we're gonna check mass. So mass is included. Now we are into environment. It says save it somewhere. I'm gonna do save it somewhere. Left and now save it here. If you just say left and YouTube. Save. It's funny. See, it's running the steps. That's so quick. Now it's ready. This is on dead load. So if you want to find natural non-zero time history function values will be ignored. It's okay. That should be. So you go here, your model 1. See, this is your T 0.046 minus 0.045 something, 0.046 here minus 0.059, which is very close. This is from, then it's from time and condition, more accurate. And if you want to get this omega, you're going to display, show tables, structural in output, model, this guy, time period. It's on the way. Model 1, time period is 0.04624 seconds. Frequency is 21.62. I got 21.7 from the lab result. It's pretty close. Natural circular frequency 135.87, 136 here. So that means gives less resonance. It's not, the model is different, but it's okay. You can always change. Let's see eigenvalue numbers. Now we know how we got these, and if you're going to go to different models, see model 2 is this way, model 3, model 4. But that is it for the model part. Now is the fun part. We are interested in that column. Right at the middle of the column, I want to know what it is. So, do this always. And maybe do this one with the animation with that pulsating load. Start animation may take too much time, but see here that's bulging out is, look at the tab says 99, that is your joint number. Joint number 99, you go to display, show plot function, and if you don't know that, you don't want to click on it, you just go on display. This guy joint labels, it shows all the joint numbers. See, this is 99. Very tiny here, 99. Display function is 99. That comes over here. On 99, we want displacement on x-axis. You can go the loadings this way, but it generates movement like this. You can get this. This is on z, uz. Uy is that way. Ux is this way. So I'm interested in ux. That's what I've done by hand. Ux. It is 3 to 6 months to solve it and program run Excel, manual Excel, doing the same thing as SAP does, almost same thing. I was positive and impacted both at the same time. So in my equation of motion, I had both. And I used consistent mass. You know what lump mass, SAP is based on lump mass. So this is the one. Here you can set to 1 second, up to 2 seconds, up to 3 seconds. But by default, it's 5 seconds. Because if you remember, we calculate the time steps up to 5 seconds. So it's pulse. See this display. That is what is happening. See, damping works here. It slows it down. It should have had resonance. But first of all, the resonance we got is for the whole building, which is the top floor. There's acting more at the top floor, not at the bottom floors. That's what's happening at the bottom. If you want to do impact, it shows you what the impact is. See, the impact impacts it a lot, and then it resonates. So if we go to 0.5 seconds from the impact load, that's what's happening. See, load, pendulum hits, that's the deflection, 0.105. And at 0.18, and it comes down and then resonates. But let's check this 76, joint 76. Display this guy. This is 76. By default, it is x-axis. I just want to show you one more time how to check this. Displacement on x-axis. Yep, from pulse. See here, damping is almost happening. So when you see this kind of looping, if you go to more time, you see loops like beats going up, down, up, down, up, down. That means you're very close to damping. Let's do real quick. You know what? Look, we put in this number here. This number, this number, this number. Write it down. 0.04624 into our Excel sheet. See this number? 0.0 is very sensitive. If you are off by a decimal, resonance doesn't happen. 0.0624. Maybe we want to get an accurate number. Go to display tables. This guy already did 0.06244. So 2 fours. 4. Now this is changed to delta t is equal to 0.000156. And I gotta take this, Control C, and go to my pulsating axial load, Control A, delete, Control V, Control S, close it. Now, we go back here. And SAP doesn't let you change your time history while it's in use. So here, just for the sake of updating, we change our pulse to impact for a second. Modify. Yep. Yeah. Define time history. This guy we deleted. Put in another one. Add new. Which is pulse for T resonance. For those who don't know, resonance is like if you have a kid, when you take them to a playground and swing, is like when it comes like you push it, it goes higher and higher and higher in buildings. It goes here, 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 and goes crazy. Because the time you push it, the delta T, is the same as the natural frequency of the building. And it resonates, duplicates. File name, this guy here, these two. What did we put as delta T? 10056 here. C file 1001561. Good way to check is go to your delta T here, 0.046. It should give you maximum load. 0.046. 624. Yeah, this is our delta. This is 389. It's higher, as we know how we know how big it works. And if you remember, I had this took a few seconds. More than a few seconds, but a few seconds. So if you put 0 damping, your resonance goes like it goes crazy, linearly increasing. If you put damping, it goes like this, and then constantly doing this. Okay. So for undamped, it linearly goes up differential. Like it's like the swing. You push it constantly with the same force. The swing, if it has 0 damping, in a few seconds, it should go through 60. But because swing has damping from friction and wind and other stuff and gravity, the constant push, it goes higher, 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 and then it stops at a level of your force is constant. It's like here, 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 and then it's going on here. So that means the displacement go up, 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 and then concentrate at resonance. That's what we should see here. Now we go define locus pulse, modify, put in the new pulse. Back in damping 0.002. Now we should be good to go. I didn't update the impact because I'm more interested in the pulse. It's running pretty quick. Oh, I didn't change the delta T time. Let's just go back. I think you guys know what I mean. Define locus. So I unlocked it again. Here, this is changed to 0.00156. See, divided by this guy. Yes. 0.00156. King. It's going. I know it is going to be a long video to upload on YouTube, but you know, I want to show you guys the most I can and myself because our conversation next week will be 4 minutes. So now let's show this baby like this. Display, joint labels. Yep. So this resonance should happen at 76. 76, the display, moment through. 76 is already here. Pulse. Yeah, see, it's going up, up, up. We need more time to show the full resonance. That resonance may not happen here or here, or may happen very late. So if you look at 99, it is not happening. If, no, I'm sorry, guys. I'm really, really sorry. What I'm gonna do, I increase the time here. So I say Control C, we go to, let's get 15 seconds. That's the number of the steps we on for 15 seconds, and then go. So. Couple more minutes, bear with me. We look at this. This display. 79, 76. This guy here, 76. It's already there, but I just want to show you what I'm talking about. 76, this time goes up to 15 seconds. Yeah. See, it is coming down because our forcing function was up to 11 seconds. So we don't want to go beyond that because forcing function stops here. Easy result after 11 seconds. Yeah, that is our damping. It's going up, 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 up. Still needs more time to go straight. That's what it will happen eventually. We look at second floor, joint 77, this here. Let's see what happens here. 77. And you can in, but stop resonance. So here the resonance, let's look at this baby. This baby, verse 78. Joint 78 display, 10, 78, come in, out. See, the first floor is really stiff. It doesn't surrender. See, it's this kind of weird shape. It's almost resonating, but no. If we look at the corner ones, let's say 60 here or 54. Display 60 for us. 60. It does. How do you output the data? That is the good question. You select your joint. For example, this one, joint 76. Go to display, tables. What do you want here? You want our pulse only. Pulse only. Step by step. It gives you all the increments and you can put it in the Excel sheet. And what you want here, we don't want this. You want joint output, displacement, and the selected joint only. Show. This is the table loading. It is loading because our contact is so small, 0.0001156 seconds. Just to check if there's any joints included, you click on this. It's just 76. This is our delta T time, which is displacement on x-axis, on y-axis, on z-axis. Yes. Rotation on x, on y, on z. So file, export to Excel. It does export to Excel. Join 76. It should pop up in a few seconds. Shouldn't take long. But believe me, it took me a good couple months to come out from what I do for you guys in less than an hour. So please share with other people. I don't need viewers, likes, all those kind of stuff, but I just want to share the knowledge. So this is the Excel sheet. This is your delta T time. This is on x-axis. So we do insert. We do this. Please don't do this. It automatically tries to pick the columns for you, but I don't want that. I do not want that. More time. You have to be drive. Yep. So I knew this. And I do select data. And this baby is good. I think easier to delete this. And it says not responding because my computer is not that big. It was kind of almost done. Show me. You have to just go from where the head is. And so do this one. Yes, please fast forward it. Events. Yeah. Right click, select data, add x-axis, we put in time, on y-axis, we put in displacement on x-axis. This is a displacement. We say we want to 11 inches. This is our displacement on x-axis. If you on y-axis, this is y-axis. What it is doing on y-axis. What it's doing this way is this column. So it resonates on this direction x-axis. Okay, everyone, have a good day. If I forgot something, I'm sorry. Stop sharing.